In exercise 18.8, we're going to use that little table that we developed in the previous video to find out whether a molecule is aromatic, anti-aromatic, or non-aromatic. And remember, if something's aromatic, that means that it is especially stable. If it's anti-aromatic, it's especially unstable. And non-aromatic compounds have an average stability. They're not extreme in either direction. So that little thought process is how we're going to go. So first we ask ourselves, are there parallel p orbitals on every atom in the ring? And because in order to form these conjugated pi bonds, each pi bond has to have two parallel p orbitals on the two carbons. You could see that all the way around the ring, for every atom in the ring, there are p orbitals that are parallel for each of these. And so the answer to that question is going to be yes for this compound. Next question, are there 4n plus 2 pi electrons? We discussed the significance of that in the last video. If there are, then the molecule is going to be aromatic, it'll be especially stable. And if there's not, then the molecule will be anti-aromatic, it'll be especially unstable. Remember, 4n plus 2 is summarizing a pattern, a series, an infinite series. The series is 2, 6, 10, 14, etc. You get 2 if you plug 0 in for n, you get 6 if you plug 1 in for n, you get 10 if you plug 2 in for n, and so on. N doesn't represent a physical thing, it's just summarizing this pattern. So how many electrons do we have in p orbitals? On this molecule, that's going to be the same as the number of electrons we have in pi bonds. So here, we can see that a little bit more clearly. If we get rid of the p orbitals, we have 2, 4, 6, 8, 10, 12. 12 electrons in p orbitals. That is not one of these 4n plus 2 numbers that are called Huckel's numbers. So we don't have a Huckel's number of pi electrons, and so this molecule is going to be anti-aromatic. It would be especially unstable. So anti-aromatic. This molecule would explode in your face, or you would just never see it because it would react with something immediately when it's formed. It's anti-aromatic. Go through the same process with this next one. First question, are there parallel p orbitals on every atom in the ring, and all the way around a ring? And so because of the conjugated pi system, we do have parallel p orbitals on every single atom in this ring. Each of the pi bonds requires two parallel p orbitals on each of the carbons, and you can see that means every single one of those carbons has parallel p orbitals on it. So yes. So then we go to the next question. Do we have a Huckel's number of electrons? Do we have 4n plus 2 electrons in those p orbitals? So let's get rid of the p orbitals just so we can see the electrons a little bit more clearly. Here we have 2, 4, 6, 8, 10, 12, 14. We have 14 electrons in those p orbitals. 14 electrons is a Huckel's number. That is one of those numbers of electrons that gives you a stable all paired electrons in the molecular orbital. So you get 14 when n is 3 in this series. When n is 3, 4 times 3 is 12, plus 2, that's 14. That's how many electrons we have here. So we do have that. You'd expect this molecule to be aromatic. In other words, you would expect it to be especially stable. Oops. If we do go through the same process for C, first question, do we have parallel p orbitals on every atom in the ring? And we do have that because of the conjugated pi system. Each of these double bonds is happening because of two parallel p orbitals on each of those carbons. That's what's causing those pi bonds. And so every single atom in this ring has that parallel p orbital. That means that those electrons are going to be able to fly all the way around this ring. And you'll get waves that are not localized in between two carbons, but they're delocalized around that whole p orbital system. So because we do have that, the next question is going to be, are there 4n plus 2 electrons in the p orbitals? Is the number of electrons that we have one of those Huckel's numbers? Is it a number represented by the series? If it is, then it'll form a stable, they'll fly in stable molecular orbitals, and if it's not, then they won't. So we have 2, 4, 6, 8, 10, 12, 14, 16. So 16 electrons in the p orbitals. Is that a Huckel's number? Well, let's see. If n is 3, then you have 4 times 3 plus 2, that's 14. If n is 4, that's 4 times 4 plus 2. The next number in the series is 18. Notice how you skip over 16. So there's no whole number you could plug in for n and get 16. So this is not a Huckel's number. So you'd expect this molecule to be anti-aromatic. You'd expect this ring to be extremely unstable. Now in rings that are this large, most of the time if you have a small ring, the ring, if it's anti-aromatic, it'll just react with something. So the species just won't exist for a long time. But if you have this large of a ring, usually what will happen is the bonds will rotate enough so that those p orbitals start to point in different directions. I drew them in as if they're all parallel, like they're all py orbitals, but if that gives rise to these unstable wave patterns, then the bonds will rotate just a little bit, and that'll put the p orbitals, that'll mean they're not parallel, and so that'll interrupt the molecular orbitals, and that'll destroy the anti-aromaticity. In other words, small anti-aromatic rings usually are just really reactive, but the large ones, most of the time, those will bend into different shapes so as to interrupt the molecular orbitals being formed by the p orbitals, so that the p orbitals aren't parallel anymore. And so those large rings will tend to exist. They'll be relatively stable. They just won't be flat. In other words, the p orbitals won't be parallel, and so they don't have those molecular orbitals being formed by them. But for our purposes on a test, all you would want to do is go through this flow chart and ask yourself the same questions we did here. If there are parallel p orbitals all the way around the ring, then go to the next question. Ask yourself if there's a Huckel's number. If you have it, it's aromatic. If you don't, it's anti-aromatic. And there won't be any exceptions for our test. But just to note that as you go through life, if you're looking at different molecules, these large anti-aromatic molecules, you might see them existing sometimes, but that's just because the bonds rotate so that the p orbitals aren't parallel, and you don't get the molecular orbitals that lead to anti-aromaticity. Otherwise, this question is really just a matter of going through that flow chart that we developed in the previous video.